Hello and welcome everyone to week 7 of problem solving session for NPTEL course Introduction to Operating System. And this week we have discussed about deadlocks, and in today's quiz we will be solving problems related to the topics we studied in week 7. So first of all, let us look at this problem, which is me a minute. Okay, consider a system with the above resource allocation graph. It's not coming correctly. Consider a system with the above resource allocation graph. So this is your resource allocation graph. R1 is a resource, R2 is also a resource, and R3 is resource, while P1, P2, P3, and P4 are the processes. And as you know that the arrow from the process to the resource means that the process is requesting the resource, while a arrow from the resource to the process indicates that the process holds that resource. And then there are dots in these resources which are representing how many units of the resource are available. Like 2 units are available. There are 2 units of resource R1, there are 4 units of resource R2, and there are 2 units of resource R3. And this is your allocation graph which is given to you. The safe sequence of execution for the processes in the above figure is. So you are given here few options, and we have been asked that if you allocate the resources in the sequence, then which one of these is a safe sequence. You have option A, B, C, and if none of them is a safe sequence, then you can choose option D, which is deadlock occurs. So now let us look at each of these sequences one by one. So first is P3, P1, P2, P4. So let me just copy this in on the whiteboard here. Okay, I'm not able to copy the image. Okay, I'll try to make the image while you can think about the problem. Okay, now I have drawn it here, and let's look at it. So here I have drawn the resource allocation graph, and um, I have here two different kind of arrows. One green ones are when the resource is being held, the process is actually holding a resource, and red ones means the process is requesting a resource. So here we can see that P1, for example, is currently holding 1 unit of R1, 1 unit of R2, and it is requesting for 1 unit of R1. Okay, so let us look at the first sequence and see if we can allocate the resources to all the processes without a deadlock with this sequence. So first P3 process, if we allocate the resources to P3 process, let's see, can we do that? So P3 here is requesting for one resource of R3 and for one resource unit of R2. So yes, we can do that. So let me just, I'm not going to erase these, I'm just going to put a small cross here, and the cross here is going to okay, not a cross, maybe let me just put here a tick, or so let me just put a tick here which says that okay, the request is allocated, the request is served, and this resource here we have taken. Okay, so this resource here and this resource here, they're no longer available, they have been taken by process P3. Okay, so now all the resources, all the units of resource R2 have been allocated, all the units of resource R3 are also allocated, and of R1 are also allocated. But then P3 will become, P3's had these two requests, and those, it was requesting 1 unit of R2, 1 unit of R3, and those are served. I mean, both of them have been, we have been able to give 1 units of these resource to P3. So P3 will execute, and when it finishes, it will free the resources that it has. It will release the resources that it has. So that means this resource will become free. This resource will also become free when P3 has executed. And after that, this resource was there with P3. So this resource will also become free. So now we have 2 units of resource, we have 2 units of resource R2 free and 1 unit of R3. Now let's say P1. Next P1 is execute. P1 executes. So when P1 executes here, it is requesting 1 unit of R1. But units of R1 both are occupied. So that cannot be. So we cannot fulfill this request. That means if we, that's a deadlock, so we cannot fulfill request of P1, and therefore P1 will not finish execution. And so this sequence is not a safe sequence. Now if we, let's look at the next sequence, which is P2, P1, P4, P3. So P2 executes first. So if, let me first redraw the arrows that was there. So this arrow was there already, and I'll make it red arrow again. So this was the original allocation graph that we had, and here P2 is executed first. So when P2 is executed, we will, let's see if we can serve, we can fulfill its request of resources. So it is requesting 2 resources, 1 unit of R2 and 1 unit of R3. So we can service them because we have 3 units of R2 and 3 units of R3. So we will service this, and then P2 will execute, and it will finish execution. When it finish execution, it will release the resources that it has. So this resource will become free, this will also become free, and it will also release this resource and this one here. So then P2 will be finished, P2 will finish execution, and it will release these resources. So now we have 2 units free of R3, 1 unit of R1, 1 unit of R2. Okay, So after that, P1 is executed. So when P1 executes here, it is requesting 1 unit of R1. Now we have 1 unit of R1 here available, so that means we can service this request. So that means we can serve this request. So we can allocate this resource here. Then P1 will also finish execution. When it does, then it will release the resources. So it will release this resource. Here it will also release this resource, and it will also release this resource. So then we have now 2 units of R1 free, okay, and we have here 2 units of R2 free also. Next, P4 executes. So if P4 executes, P4 is requesting 2 units of R2, and we have 2 units R2 free, so we can give those 2 units of to P4, and after that it will also finish execution, and when it does, then it will release the resources. So it will release all the units of R2 that it has. So it has 3 units of R2, so it will release them, and then it will 3 units of R2 will become available. So P4 also finished execution. Lastly, P3 is there. P3 is also requesting 1 unit of R2. Sorry, here there's 1 unit. So P3 is requesting 1 unit of R2, 1 unit of R3, and we have enough. Like we have 3 units of R2, 2 units of R3, and we can service this request. So P3 will be able to occupy all the resources it needs, and then it will also finish its execution. And then in this way, this sequence is a safe sequence, because all the processes, if we allocate the resources in this way, in this order, then all the processes will eventually get resources, and they will finish execution. So option B is here the safe sequence. So answer here for this problem is option B. Okay. And you can check option C as well, but this will also, because P3 and P1 they are coming in this order, and as we saw earlier that if we service the request of P3, then we cannot service the request of P1. So C option is also not a safe sequence. So option B here is correct. And moving on, next problem here is, consider a situation with the dining philosophers problem having n philosophers. What is the minimum number of forks required to prevent a deadlock? So here your options are n minus 1, n plus 1, and 2n. So the dining philosopher problem, the setting is that there are, like here, there are n philosophers, and then there are forks that are kept there, and a philosopher can be in 3 states. It can be in thinking, hungry, or eating state, and whenever the philosopher is hungry, then the philosopher will take 2 forks to eat. Okay, so every philosopher needs 2 forks to eat. And if there are n philosophers, then the question is that what is the minimum number of forks required to prevent a deadlock? Okay, so let us look at it. So consider this setting here. Let's say instead of n, here I'm just choosing 5 to give an example. If there are 5 philosophers, and these uh, violet here circles or ovals, they represent, say, the forks. So there are 5 forks. So if there are only 5 forks, then it may so happen that all of the philosophers become hungry at the same time, and then they will try to pick the forks. And every one of them, if they pick, say, the left fork first, then P1 will pick fork, this one, F. Let me just number them also. So we can say this is F1, F2, F3, 1 second, F1, F2, F3, F4, and F5. So then P1 will pick fork F1, P5 will pick fork F5, and so on. So they will pick the fork which is on their left, and everyone will have only one fork, and none of them will be able to eat. Now, of course, you might have studied ways by which we can like use the semaphores, monitors, etc., other synchronization primitives, and then we can ensure that uh, 5 forks here are enough. Like if one philosopher is in the will take the lock, and then it will try to pick the forks on both the sides, and at the same time if another philosopher on its left or right also tries to go from to the hungry state and tries to pick, then it will not be able to do. So you have seen solutions to this problem, that the deadlock can be prevented with the use of semaphores or uh, monitors, etc. But the question here is much more simpler. The question is just asking that if there are n philosophers, what is the minimum number of forks required to prevent a deadlock? Um, the question here, definitely you can have solutions really with the help of semaphores, that n forks also. If you give, then you can prevent the deadlock by using semaphores. But what is the minimum number of forks that is required to prevent a deadlock? The question simply is asking that if, like basically, if you do not use anything else, no other synchronization primitives, then what is the minimum number of forks required to prevent a deadlock? So you need here one more fork, and let us just put it here, F6. So you need one more fork. So if it happens that all of them become hungry at the same time and all of them pick their left forks at the same time, then one of them or all of them will try to pick the fork F6. Okay, and of course only one of them will be able to get the fork F6. It's something which cannot be divided, so everyone will try to pick the forks first, let's say on their lefts, and after that they will also try to pick the fork F6, and only one of them will be able to pick it. So let's say if P1 wins and P1 gets the fork F1 and also the fork F6, P1 gets this fork and also this forks, then P1 will be able to eat. And when P1 has finished eating, then P1 will release the forks, and then these forks will be available, and then say P2 will be able to get the F1 fork, and it already had F2 fork, and then it will be able to eat. So if there are 6 forks available, then there will be no deadlock. So generally we can say if there are n philosophers and if there are only n forks, then deadlock can happen. But if we have one extra fork, n plus 1th fork, then one of them will be able to get that fork and will be able to eat. And when that philosopher is done eating, it will release the forks, and then another philosophers can also get the forks they need and they can eat, and deadlock will not happen. So the answer to this question here is n plus 1. That you need a minimum n plus 1 forks to prevent deadlock if there are n philosophers. Okay, so moving on, the next problem here is that a system has 5 processes and 3 resources A, B, C. The maximum count of resources are 10, 5, 7. Consider the following table of resource allocation. And the question is that the above allocation result in unsafe state of the process, and you have to say true or false. And then consider P1 has made a request of 102, then what will be a safe sequence? So these are two related questions, and here you have been given 5 processes and you have been given the resource allocation request of these processes, which is the maximum, how many resources they can request and how many resources have already been allocated to them, and maximum count of the resources is this. So let us solve this problem first, which is saying that consider P1 has made a request 102, then what will be a safe sequence? Which of these is a safe sequence? So the problem here is similar to the first problem that we solved, but it is just been given in the form of this allocation matrix. So let us first copy this allocation matrix here. Okay, again, I'm not able to copy this. So you can look at the problem while I will write the matrix. Okay, so here I've copied the matrix. Okay, so let us look at it. Yeah, so we have been given here that the total resources we have A, B, C, we have 10 units of A, 5 units of B, and 7 units of C. Okay, and this is the allocated matrix, which means that out of these total resources, we have already allocated some units of these resources to some processes. Like we have allocated 2 units to P1, 3 units to P2, and 2 units to P3 of the resource A. So this is the allocated. So first of all, let us count that how many units have already been allocated. So here 2 plus 3 plus 2 is 7. So we have already allocated 7 units of resource A. Then for B, we have allocated 2 units, and for C, we have allocated 5 units. So we have already allocated 7 to 5 units of ABC resource. Now how many are available? So available resources are 10 minus 7, 5 minus 2, and 7 minus 5, which is 3, 3, 3, 3, 2. So 3 units, 3, 3, 2. That is 3 units of resource A, 3 units of resource B, and 2 units of resource C are available. Now that is the available resources that we have. So with this, we have this many available. These are allocated, and these are the maximum that is required. So what is the request? So how many are requested? So we can write here one more column, requested. So requested will be the difference of maximum minus allocated. So let us write that for all the processes. So we will have 7 minus 0, 7, 5 minus 1, 4, and 3 minus 0 is 3. So that means process 0 is requesting 7 units of A, 4 units of B, and 3 units of C. Okay. Okay. So then For P1, we have 3 minus 2 is 1, 2 minus 0 is 2, 2 minus 0 is 2, then 9 minus 3, 6, 0 minus 0, 2 minus 2, 0, 2 minus 2, 0, 2 minus 1, 1, 2 minus 1, 1, 4 minus 0 is 4, 3 minus 0 is 3, 3 minus 2 is 1. So this is our allocation matrix here. Sorry, requested, how many units are requested of each of the resources by the processes. So then we are given that if P1 is given, the P1's request is serviced first. The P1 has made a request of 102, then what will be a safe sequence? Okay, so P1 has made a request of 102, so that means we will be able, here we have resources 332, so we will be able to give 1 unit of resource A to P1 and 2 units of resource B, C to P1. So then P1, this request of course we can service, and after servicing this request also P1 will need 2 units of resource B as well, so that also we can service because we have 3 units of resource B here. So after this, the available units of resources I'm going to write here will be, we have given 1 unit of A, so that means 2, and we have given 2 units of B, that is 1, and we have given 2 units of C, that is 0. So after servicing P1's request, we are left with 210 resources. Okay, so then after this, we have serviced all the requests of process P1. So that next, look at if P2 makes, so let us look at this here. Then if we try to service the request of process P2, but before going here, let us see that, okay, we have serviced the request of process P1. That means we have allocated these resources to P1. Now P1 finishes, and when it finishes, it will return back the resources. It will release the resources. So it will release 1 plus 2, 3 units of A, 2 plus 0, 2 units of B, and 2 plus 0, 2 units of resource C. So we will add all of these to available, and our new available will be here. If I write, a new available will become 2 plus 3, 5, and 1 plus 2, 3, and 0 plus 2 is 2. So now we have 532 units available after process P1 has finished execution. Now if P2 is executed next, so it needs 6 units of resource A, but we have only 5 available, so we cannot service P2. So that means A is not a safe sequence, option A is not a safe sequence. So let us look at option B, which is P1, P3. So P3, let us try to see if we can service the request of P3. So P3 here is requesting 0 units of A, 1 unit of B, 1 unit of C. So which we can definitely service because we have 5, 3, and 2. Okay, so then if we service this request, then the available units which we will have will be 5, 2, 1, because we have given 1 unit of A, B, and 1 unit of C. So after that, P3 will finish execution. And when P3 finishes execution, it will release the resources that it had. That means it will release 2 units of A, 1 plus 1, 2 units of B, and 1 plus 1, 2 units of C. So all of that, let us add to the available units, and then our available units, which I will write here, will become 5 plus 2, which is 7, and 2 plus 2, 4, and 2 plus 1, 3. So now we have 743 units of resources available. after P3 is finished execution and released all the resources that it had. Now we can execute P0 or P4 according to the options. So let us see if we can execute P0. So P0 needs 743 resources, which we can execute definitely, and P4 requires 4, 3 and 1 resources, which also we can uh, service here. So if we service the request of P0, which is 743 here, then P4 we can service the request here. Okay, so we can service this, and then after that it will release the resources. So it will release 7 units of A, 5 units of B and 3 units of C. So that means we will then have, so remember here you've given all the units, so you available will be 0, 0, 0. And when P0 finishes execution, then you will have 7, 5 and 3 left. That is when we executed P0. And then we can execute P4 definitely, because it requires 4 units, 3 units and 1. So definitely we can execute this, and then it will release these resources that it gets plus 2 units of C. And finally we can definitely execute P2 because it requesting only 6 units, and we have like 7 units here. So we can execute that. So this B option here is a safe sequence, and so B is a safe sequence. And similarly, here we could have executed P4 in place of P0 also, because it requires 4, 3, 1 units, and we had 7, 4, 3 units available. And after you have executed P4, then your resources are only increasing. The available resources are only increasing because it is releasing 2 units of C. And so then you can execute P0 also, if and then finally you can execute P2. So B and C both are here the safe sequences. So option B and option C both are the safe sequences. Okay, so both of them are the safe sequences, and the question here is that this allocation results in unsafe state of the process. No, like there are allocations which do not result in the unsafe state of the process, and hence this is false. Okay, moving on to problem number 5, which is saying that consider a system with 6 processes where each process needs 2 copies of resource R. Okay, so there's 6 processes, each needing 2 copies of a resource. The maximum units of R required to cause a deadlock is dash. So this, think of it similar to the dining philosopher's problem, but here we have 6 processes. Okay, P1, so consider that you have these 6 processes and all of them need 2 units of a resource R. Okay, so this is your resource R, and let's say we have, so question is maximum number of units of R required to cause deadlock. So if there is only 1 unit of R, then and each of them needs 2 units of R. Okay, so this requires, so it is requesting, like each of them is requesting 2 units of R. So let's say if there is only 1 unit of R available, then we will give this 1 unit of R to say process P1. Okay, and so if we give this 1 unit of R to process P1 here, then still no process will make any progress because the P1 needs 2 resources, 2 units of resource R. It got only 1 unit of resource R, so it will not be able to make any progress. Now, if we had 2 units of resource R, let's say, if we had 2 units of resource R, then definitely one of the ways to allocate is that we can give this unit to P1, and then P1 will finish execution, and then when it releases both the resources, then we can give both the resources to P2, and then when it finishes, we can give both units to P3. But a deadlock can also happen here because P1 requested 1 unit, P1 requested resource R, and we gave 1 unit to P2, and at the same time all of the other processes are also they are also requesting, so it may so happen that we give 1 unit to P2. So we will give 1 unit to P1, 1 unit to P2. And similarly, if we have more units, then we can give one unit to all of them. That is, if we give one unit to all of them, then still there will be a deadlock. Still none of them will be able to make any progress because each one of them will have only 1 unit available, and 1 unit they're still requesting. Now if we have one more resource available, one more unit available here, then one of them will be able to get the second resource that they are getting and they will make progress. But if we have only this many resources and we have given 1 unit to each of the process, then they are still deadlocked. So that is, if there are 6 processes and there are 6 units of resource R, then there will be a deadlock. But if we have, say, one more unit here, then this unit we can give to one of these processes, say P5, and then P5 will be able to finish execution, and then when it finishes execution, then 2 units will become available, which will be taken by any of the other processes, and they will also eventually finish execution and give it to the other processes, release the resource, and will be taken by the other processes. So if there are 6 resources, then there is a deadlock. If there are 7 resources, then there is no deadlock. So that means the maximum units of are required to cause deadlock is 6 here. Remember that if there are 6 units of this resource, then it is not the case that there will be a deadlock all the times. There will be a deadlock only in the case when 1 unit of resource is being held by 1 unit is being held by each of these processes while they're requesting for one more unit of resource R. Okay, so here the answer is 6. So now next, moving on, we have a similar problem here, which is consider a system with 6 processes where each process needs 2 copies of resource R. The minimum units of R for deadlock free is. So as I've already explained that if there are 6 units of resource R, then there is a possibility of deadlock. But if there is one more unit available of resource R, then that unit will be taken by one of the processes. It will finish execution, release the resources that it has, and then another process can execute. So there will be no deadlock if there are 7 units of resource R. So here answer is 7. Okay, so the next problem here is problem which is 7, which is each process Pi, where I is equal to 1 to 9, is given as follows. So process P1, it's repeat. So the process will repeat like forever, sort of. And here it's like you're repeating the process, and P10 also you're repeating, like it can repeat. Okay. So what is the largest number of processes that can be inside the critical section? So there are only 10 processes here from P1 to P10, and you have been asked that what is the largest number of processes that can be inside the critical section. So for process P1 to P9, their first instruction is a semaphore down on the mutex, and this one, and then you enter the critical section, and then there is a up on some other mutex. Okay, so these, remember, these two are different mutexes. The capital one and the small one are, they're different. And on process P10, the first instruction is an up, V mutex, and then you can enter the critical section, and then there is also an up on different mutex. So what is the largest number of processes that can be inside the critical section? So here, first of all, process P1, it can say it does this. Let's say the process, say the value of the semaphore here is 1, okay, and so process P1 or the mutex, since the mutex can take here only two values, 0 and 1, so initially let's say the mutex here is 1, and then a down will make it 0. So let's say process P1 down does a down, and then it will enter the critical section here. Then if P2 tries to enter, then it will not be able to enter, it will be blocked because mutex value is already 0. But P10, so process P10, if it executes, then it can, there's an up, so it will do an up, and then it will enter the critical section, and it will make the mutex 1. So that means process P2, which was earlier trying to enter the critical section, will now be able to enter the critical section. So in this manner, let's say P1 is already in critical section, P2 is there in the critical section, and now P10 is already in the critical section. Now if P3 tries to enter, then P3 will not be able to enter because the mutex is still 0. But if say P10 finishes execution and it comes out, and then if it does again an up, so then P3 will also be able to enter, and then P10 will also enter. So in this manner, if first P1 executes, or some other process out of P1 to P9 executes, and it does a down, making the mutex value 0, and then if P10 executes, then it will make the value of mutex 1, it will do an up. After that, another process from this set can enter, and then P10 executes again. So if a process from this set executes, that enters the critical section, after that, if we execute P10, then another process from the set can execute. So basically, it will be like an alternate between a process from this set and P10. So first P1 executes, then P10, then P2, then P10, then P3, then P10. So in this manner, every time P10 gets it enters the critical section by doing an up on the mutex, thus thereby allowing some other process to enter the critical section too, while some other processes are already in the critical section. So in this manner, all the processes from P1 to P10 can get inside the critical section at the same time. Because process P10 can repeatedly execute, and on every execution it is doing an up operation, while so if a process is blocked, then it will be able to enter. So the largest number of processes that can be inside the critical section is here 10. So the answer here is 10. Okay, so moving on. Next problem here is that consider a system has 3 processes, P1, P2, P3. Process P1 needs 11 units of resource R P2 needs 21 units of R and P3 needs 16 units of R. What is the maximum unit of resource R that leads to deadlock? So when does a deadlock happen? A deadlock will happen when the requests of all the processes are not fulfilled, okay? And we do not have any free resources to fulfill those requests. So if P1 is requesting 11 units, so it should not be able to get all the 11 units. P2 requests 21 units, it should not be able to get 21 units, and P3 is requesting 16, it should not be able to get 16 units. So, and we have to find the maximum unit of R which are available but still leads to deadlock. So that means at least one unit of resource should not be available to each of the processes. So if 10 units are available to P1, but 1 unit is not, it will still make the process wait for that resource. So if we give 10 units of R to P1, 20 units of R to P2, and 15 units of R to P3, and then there are no more resources available, that means all of them will be requesting one units, 1 units each of the resource, and they will still be requesting, and that will be a deadlock. Like here, what I'm saying is that if P1, P2, and P3 processes are there, and this is our resource R. So if we give 10 units of resource R to P1, we give 20 units of resource R to P2, and 15 units of resource R to P3, and then we know that they need 11 units are needed by P1, 21 units are needed by P2, and 16 units are needed by P3. So they will still be requesting for 1 unit, okay? And in this way, all of them are deadlocked because they're holding the resources while they're waiting for more resources, and the resources are not available. So they are deadlocked. Okay, so then how many resource units are there? So there are 10 plus 20, 30 plus 15, 45. So 45, if we have maximum 45 units of resource, it can still lead to deadlock. If we have 46, it will not lead to deadlock, because if we have one more unit here, then if we had one more unit of resource somewhere here, then that resource we could have allocated to one of these processes, and then that process would have executed. After finishing its execution, it would have released the resource, and then those resources would be available for others to use. But if we have only 45 resources, then that still causes a deadlock. So the answer here, the maximum units of resource R that leads to deadlock is 45. Okay, so the next problem is, which of the following is false about user threads? So first is, user threads can switch fast since it does not involve kernel. Second is, user threads are lightweight since they do not require system calls. Third is, kernel is not aware of the behavior of every user thread, that is, if it is blocking or runnable, and D is none of these. So which of them is false about user threads?